Okay, so now that we have the basic algorithm or the method of multiplication of matrices, let's talk about how we can use Excel or maybe even R, because when the matrices get big, we don't want to do this by hand. All right, so let's go over here. So we have our A matrix, 3, 2, 1, 1, 4, 0, and we have our B matrix, and we have the number of columns 2 matching up the number of rows, 2 columns and 2 rows. So we set up the results as being the number of rows in the first 3 times the number of columns in the second 2. And we can go M for matrix multiplication in Excel. And we're going to do the first array, comma, times the second array. And if we hit enter, this, oh man, we don't have, this is what we get. So when we use arrays, what we need to do in Excel is go Control Shift Enter, and I guess in Max it'll be Command Shift Enter. And here's our result. Oh, good, it's the same answer I got. All right, so now that we have the matrix multiplication down, we can go back to our simultaneous equation up here, and we can write this in matrix form. Right, so we can have the coefficients 2 and 3 and 3 and 4 times the variables x and y, and that equals 12 and 15. And again, we have our little rules. We have a 2 by 1 matrix, or sorry, this is a 2 by 2 matrix, and this is 2 rows, 1 column. So the number of columns equals the number of rows, and we're going to end up with a 2 by 1 result. All right, so when we have the first row times this column, what we end up with is 2x plus 3y, which is what we have over there, equals 12. And then we have the second row times the column, 3x plus 4y, is which we have over there, equals 15. All right, so it makes it convenient. All right, so when we go to this behemoth right here, so basically we're going to have the coefficients, 5 by 5 coefficients over here times 5 by 1 series of variables, x1, x2, x3, x4, x5. What do we have? The coefficients up here is 1, 1, 1, 1, 1. And we have 1, negative 1, 1, negative 1, 1. So we have 1, negative 1, 1, negative 1, 1. And I guess really the first one's equal to 0. Second equation is equal to 1. Third equation, we have 3, 7, 3, 7, negative 10, 3, 4. And again, it's this column times all the x's equals 40. And then we have the fourth column. We get the negative 2, 16, 4, negative 7, 1 times all the x's equals 25. And then we got 10, 15, negative 5, 5, and 10 equals negative 8. Right, so we have 5 equations and 5 unknowns, and we're going to see a little bit later on, if we call this matrix A, I don't know, call this vector of x, a 5 by 1 vector, and this is B, we can actually find x by taking something called the inverse of A times the B. So we can do this in Excel, we can do it in MATLAB, and so, or R, anything we want. And so let's go back to here, let's look at some more rules real quick. So when we have what an identity matrix is a square matrix such that this is basically the multivariate equivalent of multiplying by 1. All right, so what it is a diagonal matrix where the diagonals are all 1. And if we multiply this by the appropriately dimensioned matrix, pre-multiply or post-multiply. See what we get. So if we have 3, 2, 1, 1, 4, what is it, 0? What we have is 1 times 3 times 0, 0. So that will give me 3. First row, second column, 1 times 1 times zeros times the others, and we get 1, and we continue on, and we get the exact result. So we can take this vector right here, or matrix, I should say. Again, this is, what is it, 3 by 2. And if we post-multiply by this identity matrix, now it has to be 2 by 2, square, and where the rows match. And what we're going to get is 3 times 1, and 1 times 0, 2 times, let's see, 2 times 1, 4 times 0, and it goes down like that. And then first row, second column, 3 times 0, 1 times 1, 2 times 0, 4 times 1, and then we get the matrix. It's the identity matrix. All right, so a ones vector is, let's say, is just in 405, I call it a vector E. So we might have a vector of ones. All right, so this is a row vector. So if I have another column vector of B, sorry, a row vector, this is a column vector, I should say, and this is 3, 2, 8. What B times E will give me, this is 1 times 3, and this is a 3 by 1. 3, 2, 8 times 1, 1, 1. So 3 times 1, 2 times 1, plus 8 times 1 will equal 13. So this ones vector, you know, just where one of the dimensions is a 1, sums up the items in the column or the row of this array over here. All right, so what else do we have? The distributive law in matrices. So let's say we have AB plus AC. Well, we can factor out the A's. And so what we have is a BC, where B and C are appropriately dimensioned. So let's say that A is a 2 by 3 and B is a 3 by 1. And so if we're adding these two things, they have to be the same sort of dimensions, 2 by 3 by 3 by 1. And so when we multiply it out, we're going to get a 2 by 1 matrix. All right, so this is, we can factor out the A. But notice, one thing we can't do is if we have an A and a B plus, let's say, a D and an A, we can't factor out the A because the side really matters. So we have the A post-multiplying by D. So D is, I don't know, some 1 by 3. I don't know what it is, but this, you can't factor out the A there. All right, so when we talk about a transpose, so what a transpose is, say we have A is our 3, 2, 1, 1, 4, 0. And when we take that transpose, or sometimes it'll be A with a T up there, what happens is when we take a transpose, the rows become columns and the columns become rows. So when we have our first column, the column shall become the first row. So first column 3, 2, 1 becomes the first row 3, 2, 1. Second column 1, 4, 0 becomes the row 1, 4, 0. Okay, so that's all the transposes. All right, so what else do we have here? Oh, the big thing we're going to talk about next is the inverse of a matrix. So one thing we'd like to do over here is, let's say we have a problem where we have ax equals b, sort of like our big problem up here. So we have this a, and then we have a vector of coefficients equals b. Well, what we'd like is the multi-dimensional equivalent of what we do in just regular algebra. We'd like to divide both sides by a and solve for x. Well, in this case, we have to be careful. So we're going to pre-multiply by something called an A inverse. And so when we have A inverse times A, what this gives us is the identity matrix. So it's basically a series of transformations of matrix such that when multiplied by A gives you the identity matrix. And so anything times the identity matrix is itself. So this A goes to the identity matrix, and identity matrix times x will give us x. So if you pre-multiply on this side, you have to pre-multiply on the other side. All right, so we'll talk about finding the inverse on the next slide, or the next set of videos, and take care.